So what we're going to look at is bonding. So some of this will actually be a recap from what we've done at GCSE, and then just taking it into a little bit more detail for A level. What you will notice is there'll be discussions and mentions of intermolecular forces and intramolecular forces. At the moment, intermolecular forces are just forces that occur between different molecules, and that's all we have to worry about for now. In a couple of lessons later on, I'll go more into depth about intermolecular forces, but it's actually easier to talk about the bonding separately and then do a lesson on intermolecular forces. So if I mention intermolecular forces, and I'll recap it when I do, it's just forces that occur between different molecules for now. And intramolecular forces are forces that occur inside molecules, and they're always covalent bonds. So we'll look in them in a bit more detail. So we're going to start off with ionic bonding. So we're going to look at how ions are formed, why they attract each other, the properties of ionically bonded compounds, and the structure of ionically bonded compounds. So we'll start off with ionic bonding. Okay, so atoms make bonds between each other by using their outer electrons. But it's this idea of why do we do it at all? Well, it's the whole principle, it's that whole idea of stability. If the outer shell of a atom is full, it is more stable. So atoms want to be as stable as they possibly can be. So by doing this, one of the ways of achieving this is by gaining a full outer shell of electrons. So this explains why our noble gases are really, really unreactive. They don't like to form bonds. They don't really do that much. They're very unreactive. They don't like forming bonds because they all have a full outer shell of electrons. And it also explains why our alkali metals and our halogens are really highly reactive. They both either need to just gain one electron or lose one electron to get a full outer shell. So that shows why they are very, very highly reactive. So one type of really strong chemical bonding is ionic bonding. Ionic bonding, you should remember from GCSE, this occurs between metals and non-metals. And electrons are transferred from the outer shell of the metal to the outer shell of the non-metal. So that's really important to remember, that we're transferring electrons from the metal to the non-metal and just on the outer shell. So if we're looking at alkali metals and halogens, for example, we would be losing an electron from an alkali metal and gaining it on the halogen to make them both have full outer electron shells that are nice and stable. The metal forms a positive ion, and a positive ion we call a cation, and the non-metal forms a negative ion, which we call an anion. And they're two words that you should be familiar with from doing electrolysis at GCSE. Cations are positive ions, our anions are negative ions, and then cations are attracted to the cathode and anions are attracted to the anode. So that's a basic general thing about cations and anions. So an ionic bond occurs between an atom of sodium and an atom of chlorine. Let's have a look at what this would look like. Here we go. Here's our sodium atom. We've got our sodium atom there. It has just got one electron on its outer shell. It's 3s orbital, just got one electron. Chlorine atom, we've got a 3p5. It's shown that we've just got one electron missing to make that a full outer shell. So what happens? Well, our sodium loses an electron and our chlorine will gain an electron. So the sodium atom loses its 3s electron to the chlorine atom. The sodium becomes a sodium 1 plus ion and the chlorine becomes a chlorine 1 minus ion. And we often draw them in the brackets with the positive and negative signs that are according to them next to them once they've become an ion. So the ions stick together. So this is the actual bonding part, because actually we've just given, one's got lost an electron, one's gained an electron, but we're actually calling it a bond. We're saying they're actually attracted to each other. So the ions actually then stick together due to an electrostatic attraction between the positive and negative charges. So it's actually an electrostatic force that keeps these two, electrostatic attraction that keeps these two atoms together, these two ions together in this situation. And it's because they have a positive and negative charge, so it's the opposites attracting again. So ionic bonding is the result of our electrostatic attraction. It's electrostatic attraction between oppositely charged ions extending through the compound so that every negatively charged ion attracts itself to every positively charged ion and vice versa. So ionic compounds always exist in a structure that is called a lattice, and we call them ionic lattices. You'll have heard of lattices before. You get giant ionic lattices, you also get giant covalent lattices, but we're going to look at giant ionic lattices first. Giant ionic lattices are made up of repeating units of identical structures. So as you can see on here, we've got repeating units of positive ion, negative ion, positive ion, negative ion. The different ionic compounds have very, very different lattices, which is really important to remember. Also, ionic compounds do dissolve in water. They dissolve in water because water is a polar molecule. So from our biology lesson earlier on this week, where we learned that water is a polar molecule, and because of its polarity and this electrostatic attraction, ionic compounds are actually dissolvable in water because of that same attraction, electrostatic attractions. And finally, ionic compounds are able to conduct electricity when molten or dissolved. If they're solid, they can't. If they're in a solid state, they can't, but when they are molten or dissolved, the ions are then able to move and then they can carry the charge, so they become a charge carrier in that situation. We're now going to move on to covalent bonding, I think. Just double check I haven't missed anything out. Oh, and they have a high, I did miss something out. I always do this with something. They also have a really high melting point because their bonds are really, really strong. We're now going to have a look at covalent and dative bonding. They're sort of one in the same of each other, but we will have a look at them. So we're going to look at a covalent bond, a coordinate bond, which is also a dative bond, and describe the properties of covalently bonded molecules. So another type of strong chemical bond is covalent bonding. Covalent bonding, this only occurs between non-metals. So covalent bonding occurs just between non-metals. Ionic is between a metal and a non-metal. Atoms share some or all of their outer electrons in order to gain a more stable electronic configuration. So it's that same idea. We're still trying to get a full outer electron shell. But in this situation, rather than gaining and losing, we're sharing. One covalent bond equates to one shared pair of electrons. That's really important to remember. One covalent bond is one shared pair of electrons. A single covalent bond between two atoms can be represented by a single line. Covalent bonds can actually come in double and triple bonds. So I haven't got it on here, but for example, if we're going to draw it with a double bond, it would be, for example, your two atoms drawn with two lines, triple bond, your two names of your atoms drawn with 3 lines. So here we go. We've got a chlorine atom. Now, chlorine atom has an electronic configuration of Ne3S2, 3p5, and here we go again. We've got some of using those noble gases to help us. So we've got neon in there. Neon is our shorthand for our electron configuration because we're basically saying its whole electron configuration is the same as neon up until this point, and then it has these extra bits. So remembering that is a good shorthand way of showing our electron configuration. So this is our chlorine atom. Two chlorine atoms would both want to gain another electron. So they can't lose an electron to gain an electron. So what they're going to do is they're going to share a pair of their electrons. So by each sharing a 3p electron, they can achieve this. And what they achieve is they both achieve having a full outer electron shell. So covalent bonding describes a chemical bond where a pair of electrons are shared between two atoms. But how does this hold the two atoms together, which is quite important. So our ionic bonding, okay, we've lost one, we've gained one, they're held together with intermolecular forces. Well, actually, how does this covalent bonding actually hold them together? It holds them together using attractive and repulsive forces again. It's working on that idea of positive and negative charges. So atoms with a covalent bond are held together again by electrostatic attraction. But this time, rather than in an ionic bond, it being between the positive ion and the negative ion, in this situation, it's between the positive nucleus with the protons in and then the negative electrons. So atoms with covalent bonds are held together by an electrostatic attraction between the nucleus of each atom and their shared electrons, and that's where you've got that positive negative attraction occurring. You can also get, these are the double bonds that I was talking about. So oxygen can covalently bond together. When it covalently bonds together, it actually shares two pairs of electrons to make a full outer shell. So it is a double covalent bond. So to draw this, we draw the two lines next to oxygen. We can also get triple bonds, nitrogen triple bonds, which means it shares three pairs of electrons, and we can also get quadruple bonds. We don't need to really worry about quadruple bonds. We don't really come across them at A level. So it's double and triple bonds that we need to really think about. So these occur when two atoms share more than one pair of electrons. We also get a coordinate bond or a dative covalent bond. It sort of has two different names, means exactly the same thing. What this is, it's a covalent bond in which both electrons in the bond come from the same atom. So rather than, if we look here for the oxygen, or even actually go further back, look here at chlorine, they're sharing a pair of electrons. One electron has come from this chlorine atom, one electron has come from this chlorine atom. In dative bonding or coordinate bonding, the electrons come from the same, both the pair of electrons actually comes from one atom. So for example, the one that we usually use is ammonium ions. So this is an ammonia molecule. In ammonia, if an ammonia molecule goes and attaches itself to a hydrogen ion, it attaches to it with its lone pair. So we've got a hydrogen ion, which obviously wants a full outer shell, but obviously that's got no electrons on it. So it shares these as a full outer, it shares both of their electrons, the ammonia does, with the hydrogen to make this full outer shell. It is represented by an arrow coming from the atom donated to the electron. So you can see this arrow going there here, showing the coordinate bond, saying that we are sharing this with this. The atom that accepts does not have to have a full outer shell of electrons. It is electron deficient. And the donating atom donates a non-bonding pair of electrons. So this is known as a lone pair of electrons. So they're not bonded with anything else. They're a lone pair. They're not doing anything else. Coordinate bonds do not differ in strength from regular covalent bonds. So for example, in that ammonia molecule, it's NH3. So those two electrons are a lone pair of electrons. They're not doing anything. Obviously, they're working as electrons, but they're not bonded with anything. So actually, they have that ability to then go and bond with a hydrogen ion in a dative or coordinate bond. Now we're going to have a little look at metallic bonding. Let me just get to my metallic bonding section. So we're going to describe the nature of bonding in a metal and describe the properties of metals. So metallic bonding, as you probably can remember, we've now done ionic bonding, which is between a metal and a non-metal, covalent bonding, which is between non-metals, and then metallic bonding, which is between metals. So metals can really easily lose up to 3 outer electrons. And if we think about the electron configurations of sodium, magnesium, and aluminium, we can see that. However, they only lose these electrons if there is a non-metal available to take them. So they would form an ionic bond. What more regularly occurs if there isn't a non-metal around, The metal will then merge the outer main levels of all its atoms together, so that the electrons are no longer associated with any one atom, but are shared by all of them. And so we basically get this thing that we call a sea of free electrons. And so all these metal atoms merge together and they just share all their electrons. And that makes them as stable as possible. So metallic bonding is actually this almost giant sharing of electrons. It makes a sea of free electrons where they're all sharing them. So the electrons aren't assigned to any one or any two atoms anymore. So this is our metallic bond. And so here's an image of metallic bonding. So our metal ions are completely arranged in a lattice again. So we've still got this lattice structure. And each metal in this case has one electron in its outer shell. These electrons become part of a delocalized sea of electrons. So what they want is to have a full outer shell. They would need two electrons in its outer shell, if we're talking about the first shell, for example, but they're not covalently bonding. They're not because they can't, because obviously they're metals, so that's not a possibility. They're not ionically bonding because actually they would then need to go have a non-metal around. There's no non-metals around, so actually we're going to metallic bond. We're going to share all of these electrons together so that at some point we all have a full outer electron shell. So we call these a delocalized sea of electrons. The number of delocalized electrons depends on how many electrons the metal atom can lose. So it depends on which group we are talking about that the metal occurs in. So this results in a giant metallic structure. So here we go. This is what I mean by it depends on what group you're in. So sodium has the ability to lose one electron. Magnesium 2, aluminium 3. Okay, so their electrical conductivity, it works because they have free electrons and they act as charge carriers. So as our ionic charge increases, our ionic size decreases and our number of outer shell electrons increases. So attraction increases, melting and boiling point increases. So as our attraction is increasing, our melting and boiling point increases. So group 2 will have higher melting points than group 1. And now we're going to have a look at, we're not going to look at bond polarity, we're just going to skip this bit. We'll come back to that in a bit. I've just done this in a different order to what I wanted. Skip that bit as well. Okay, so bonding and physical properties. We're going to have a look at the physical properties of lots of these giant structures. So we're going to state the energy changes that occur on melting and vaporization, explain the enthalpies of melting and vaporization, and then explore the physical properties of molecules and compounds in terms of their bonding. So you would often get a table like this and it asks you to show the arrangement of solids, liquids, gases, evidence, spacing. So a solid, the arrangement of the particles is regular. Evidence, well, the evidence behind that is crystals. Crystals have straight edges, so we would say that the arrangement of particles is regular. Spacing, the spacing is close. Evidence for that, well, you can't easily compress a solid, so therefore the spacing of them must be close. There's no gaps, there's no air, so we can't squish them together. Movement, they just vibrate. Evidence, they have slow diffusion, they expand on heating. Whereas liquid, the arrangement of air particles is random. The evidence behind this is they change shape to fill the bottom of a container. The spacing is close because, again, they're still not easily compressed. The movement would be described as rapid or jostling, and the evidence for that is that they have slow diffusion and evaporation. Gas arrangement is random. Evidence will fill its container. We know gas will fill its container, and that's sort of it. Spacing far apart. What is the proof of that? Well, they're easily compressed. Movement, rapid. Evidence, well, rapid diffusion, exertion of pressure, there's lots behind that. So we have our types of structures. So we can have giant ionic. So giant ionic structures giant ionic structures are classed as giant crystals or ionic crystals. So they are crystalline structures where the ions are held together by an electrostatic attraction. And they have strong electrostatic attractions between the ions. They have really high melting points. The ions are in fixed place. They do not conduct electricity as a solid. That's really important to remember, that ionic structures do not conduct electricity as a solid. And they are charged molecules, so they are soluble in polar solvents. They have no intermolecular forces. Okay, they have no intermolecular forces happening on them, just have that ionic bonding. We also have giant covalent structures. They're a macromolecule. And these are also crystalline structures. They are crystalline structures where the atoms are held together by strong covalent bonds. These strong covalent bonds stop them from being able to be dissolved. They have a high melting and boiling points, and actually many of these sublime, they completely miss out the liquid stage and go straight from solid to gas. Again, these have no intermolecular forces. Then we have a simple covalent structure, which is a molecular structure. And these are structures are rarely crystalline, and the molecules are held together by weak intermolecular forces. So actually, we've got our covalent structures, and then we have these weak intermolecular forces holding them together. And then we have our giant metallic structures. Our giant metallic structures are, again, crystalline structures, and these are where metal ions are held together by a sea of delocalized electrons. So it's a sea of free electrons, again, that we've just spoken about. These have a high melting point, and that is because of their strong electrostatic forces, and this depends on the number of their free electrons. They conduct electricity as a solid, unlike any of the others, but they do not dissolve in water. Generally, this is sort of a, in parentheses, generally they don't dissolve in water. What would generally happen with a metallic structure is if it is mixed with water, it would make a metal hydroxide instead, and these have no intermolecular forces. So an example of one of these would be, these are carbon structures actually. An example of a carbon structure in this situation would be diamond. You probably remember doing this bit at GCSE as well. So yeah, an example of that would be diamond. So the type of bonding that occurs in diamonds is covalent bonding. It is a giant covalent structure. It has very high melting points. It's very, very strong. And it's held together by very strong covalent bonds, which require extremely large amounts of energy to break. It doesn't conduct electricity because it has no delocalized electrons. So it contains no charged particles, electrons to carry its current. And we use it for things like jewelry, blades, cutting hard objects, and it's covalent bonds. So each carbon atom, so it's a allotrope of carbon, which means it's a molecule just made up of carbon. Each carbon atom is covalently bonded to 4 other carbon atoms, which makes it have this giant covalent structure. And it's hard due to its covalent bonds, high melting point, and it has this high melting point because it's very hard to break these covalent bonds, so it has a very high melting point. Also has thermal conductivity, and that is due to its rigid structure. And because of its rigid structure, the vibrations easily carry heat through their structure. So the vibrations of the atoms in this solid state easily carry heat through the structure. So it has very high thermal conductivity. Another example, which you've probably seen before, is graphite. Graphite, again, has covalent bonds involved. It is another giant covalent structure. It has a very high melting point, but this time it is soft. So what happens is it's held together by very strong covalent bonds, but these are in layers and in sheets, and each sheet is held together by weak intermolecular forces between the layers, between the sheets. Each carbon atom this time is bonded to 3 other carbon atoms, and it has a high melting point and it is insoluble in solvents, but it is very, very soft. So these layers of hexagonal rings are held together by super, super weak intermolecular forces. And the layers, what are really good about the layers is they're easy to slide over one another, and that makes it a useful lubricant. So we use it in things as for pencil lead, which obviously isn't actually lead anymore, but because of this ability to slide over, it can then make marks on paper. And it is able to conduct electricity, and it's really good at conducting electricity between the hexagonal planes. And that's because each carbon has 3 covalent bonds, and 1 electron from each carbon is delocalized. So these delocalized electrons are free to move and transfer the electrical current through the gap. So unlike diamond, which has each carbon has 4 covalent bonds, there's no delocalized electrons. In graphite, we only have 3 covalent bonds. So we have this delocalized electron, and then we have these layers that between the hexagonal sheets that the delocalized electrons are able to travel through. And we often use these graphite for electrodes and pencils. Now I'm going to sort of go back and I'm going to go through the other bits of bonding now, but I find it's a little bit better to do it in this order. So I'm going to go through polarity, bond polarity and covalent bonds now. So again, this is quite similar to what we started talking about with water the other day in biology. So we're going to look at electronegativity. We're going to look at what makes one atom more electronegative than another, and look at what the symbols mean when we place them above atoms in a covalent bond, which obviously you did see as used the other day when we were talking about water. So they obviously mean positively and negatively, positively charged and negatively charged, but in that polar part of the molecule. So forces that hold atoms together are all to do with their attraction between positive and negative. Everything is to do with forces of attraction between positive and negative. In ionic compounds, this is called by electrons being completely transferred between our atoms. Covalent bonds, it's because the electrons are shared between the 2 atoms. However, sometimes one atom is better at pulling electrons towards it than another. And what happens is, and this is where the water molecule comes in. So water is composed from covalent bonding, and the electrons are shared between the 2 atoms. However, what happens is one atom is a little bit better at pulling the electron towards it than the other, and it's to do with that positive charges of a nucleus. And so what this results in that atom having actually a greater share of the electrons in the bond. So we would say that that atom would be said to be more electronegative, because it has more of the electrons around it. And so this is how we get these polar molecules. So electronegativity is the power of an atom to attract the electron density of a covalent bond towards itself. So basically an atom is able to basically take as many of the electrons, the pull of the electrons is closer to it in that covalent bond than it is to the other atom. So when we talk about electrons, we start to consider them as clouds of charge, and we start to use this term electron density. It's often used to describe the way our charge is distributed. So we talk about electrons on our really nice orbitals and planes, and then actually when we start talking about charges and bonds, we actually can start talking about them being clouds and their ability to sort of move between here, there and everywhere. So electronegativity depends on a few things. Sort of thinking about it, this is going to be an atom that's able to attract those electrons more. Some of the reasons behind it is the nuclear charge of the atom, which makes complete sense straight away if we think about it. Electrons are negatively charged, a nucleus has a positive charge. If the nucleus of one atom has a higher positive charge than the nucleus of the other atom, it's going to have more of those electrostatic charges. It's going to pull those negative electrons towards it more. It's going to have more of a pull than the other atom. Another thing that affects electronegativity is distance between the nucleus and the outer electrons. If we think about shielding, when we were talking about ionization energies, this has an effect as well. So shielding and the distance between the nucleus and the outer electrons makes an impact. So shielding of nuclear charge by electrons in a shell. So we've got nuclear distance, we've got shielding, we've got charge. So actually these are lots of the same things that are affected ionization energies. So these statements are we can actually use them to describe and explain the trend in electronegativity across a period and down a group. So when we look at a periodic table, electronegativity decreases down a group. So it means that the atoms become less electronegative as we go down. So hydrogen is more electronegative than potassium, for example. As we go across a group, electronegativity increases. So for example, lithium is less electronegative than sulfur. So we measure electronegativity using the Pauli scale, where 4 is our largest electronegativity possible. So noble gases do not have a value, obviously, because it's unusual for them to form covalent bonds because they have a full outer shell, and so therefore would have no need to form a covalent bond. This bit down here where we have FO and Cl, it's saying that basically fluorine has a greater electronegativity than oxygen, which has a greater electronegativity than nitrogen, which has a greater electronegativity than chlorine. You think, okay, well, why chlorine? Well, chlorine and fluorine, the issue with them is fluorine has less, it's decreased. Why is it decreased? Well, because its atomic radius is increased and that shielding then will have increased. So our most electronegative atom would obviously be fluorine in this situation. So polarity then is what we use to talk about this unequal sharing of electrons in a bond. So if the electron sharing is equal, the bond is described as non-polar. So a non-polar molecule is a molecule that's got a covalent bonding, but all the electrons are shared very equally. We haven't got any electronegativity occurring. So chlorine atoms have the same electronegativity in this situation. So both chlorine atoms have the same electronegativity of 3 on the Pauli scale. Therefore, it will be a non-polar molecule. Because they're both the same atom, they're both going to have exactly the same electronegativity. So they're not going to pull the electrons more to themselves or the other because they're both exactly the same. Whereas, so the electron cloud is shared evenly between the two atoms. So this electron cloud is the area that the electrons can travel around the two atoms. So the bond is described as being non-polar. However, chlorine has a higher electronegativity, 3 on the Pauli scale, than hydrogen, which is 2.1. You can see from this image straight away, because chlorine has a high electronegativity, it is going to be a polar molecule and it's more electronegative, so therefore it will have a greater density of the electrons will spend their time over at the chlorine atom. So the chlorine is able to pull more of the electron cloud towards itself, and so therefore the bond is described as being polar. So here we go. We've got our hydrogen, we've got our chlorine. And this is what we mean by these symbols. So if the two atoms that are bonded together do have different electronegativities, this is represented using our partial charges. So they're described as delta positive and delta negative. So it's saying the hydrogen has a partially positively charged and the chlorine is partially negatively charged. So that's because they have different electronegativities. So a molecule can be made up of actually several polar bonds, but be non-polar overall. And this is about like equaling out our charges overall. So here we go with carbon dioxide. Because the molecules are symmetrical, there's no overall polarity, and the electron cloud is shared evenly over the whole molecule. So carbon dioxide, we have our 2 oxygens on either side. The actual polarity of it is the same in both directions. So actually that would be a non-polar molecule overall, even though it has polar bonds inside it. And that is the same for our carbon chloride. So what we're going to have a little look at now, I think, if we have time. Yeah. Okay. So if I just actually have a little talk about water. So we talk about water being a polar molecule. Water is a polar molecule. That is because it's made up of hydrogen and 2 oxygens. So unlike carbon dioxide, where it's carbon sharing 2 oxygens, H2O, we've got the 2 hydrogens with 1 oxygen. So the oxygen is still going to pull in the hydrogen, the electrons from the hydrogen more, so it spends more time there. And so that's how, rather than it being on a symmetrical plane, for water, it makes more of this shape, that Mickey Mouse ears that I was talking about. So if we make this sort of shape, we make more of that shape, we have that Mickey Mouse shape being made instead. That's just because of the polarity that's occurring there. So let's move that so I can actually see. Finish off then, we'll look at intermolecular forces. We possibly won't get through all of these now, but we'll start having a look at them. So, oops, why is this not working? Let's close that. So we have a few different types of intermolecular forces. These are our forces that we find between different molecules. So intermolecular forces are forces we find between molecules, and intramolecular forces are forces we find inside molecules. So intermolecular forces, van der Waals forces, or van der Waals force, also known as a temporary dipole-induced dipole force. Generally, rather than being called a temporary dipole-induced dipole, most people call van der Waals forces van der Waals forces. We have a dipole-dipole force. Also have hydrogen bonding. Hydrogen bonding is a intermolecular force. Van der Waals forces act between all atoms and molecules. Between all atoms and molecules, whereas dipole-dipole forces and hydrogen bonding can only act between certain types of molecules. As you can probably guess, hydrogen bonding can only happen between certain types of molecules that possess a hydrogen atom. They also increase in strength. So hydrogen bonds are the strongest type of intermolecular force. Van der Waals are the weakest type of intermolecular force. These are so much weaker than covalent bonds, so do not get them confused. So whilst we're calling them bonds or forces, they are really, really, really so much weaker than covalent bonds. So don't get them confused. So if we were talking about strengths of bonds, of intermolecular forces and intramolecular forces, intermolecular forces is always your weakest. Your bonds between molecules. So your van der Waals are going to be your weakest. Dipole-dipole, hydrogen bonding. Then you've got your ionic bonding, then you've got your covalent bonding, and ionic and covalent would come into your intramolecular forces. So let's look at dipole-dipole forces. Dipole refers to a molecule where the charge is shared unevenly. So it's like that polar idea. So these occur between molecules that possess an overall dipole. So for example, HCl, so hydrochloric acid. You can see here that we've got a molecule where our charge is shared unevenly. Inside our molecule, our intramolecular force is our covalent bond. It's nice and strong. But actually, our dipole-dipole is occurring between one molecule of hydrogen chloride, hydrochloric acid, and the other molecule of hydrochloric acid. So it's an intermolecular attraction, and that's a dipole-dipole force because it's between one molecule that's a dipole and another molecule that's a dipole. And it is weak. So the partially positive hydrogen part of one molecule is attracted to the partially negative chlorine part of another molecule. So it's still the opposites attract. It wouldn't be the chlorine and the chlorine attracting. It's the hydrogen, partially positive hydrogen, attracting itself to the partially negative chlorine. So it's the dipoles, it's the partially charged sections attracting themselves to each other. Lots of molecules can join themselves together in this way, But remember, these forces are weak. It doesn't take much to break these forces at all. Van der Waals forces, sometimes called instantaneous dipole-induced dipole forces. These occur between all molecules, even if there are other intermolecular forces acting on that molecule. These also occur between atoms. Basically, you find van der Waals forces everywhere. Helium, we're going to use that as our example. So helium has 2 electrons in its neutral atom, but these electrons could be anywhere at any time. They are constantly on the move. It's that idea of when we talk about gas particles, you have Brownian motion, that random distribution. That's what's happening with the electrons. They can be anywhere. It's that same sort of concept. They can be anywhere inside that atom, moving around on those orbitals at any point. So they could all be over one side, they could all be over the other. So they're constantly on the move. So we have an uneven distribution of electrons in helium. If in this direction, we would call it an instantaneous dipole, and this side is an induced dipole on neighbouring. So if they happen to both be on one side, a temporary dipole is created. This can then induce a dipole in a neighbouring atom, causing the 2 atoms to be temporarily attracted to each other until the electrons move again. So basically what's happened is we've got both the electrons on the left-hand side over here. So we've now got a temporary dipole forming. We've got a partially more negative side of our atom to our partially more positive side of our atom. Because of that, it's going to temporarily create a dipole in our neighbouring atom, and it causes them to be temporarily attracted to each other until the electrons move again. So it isn't permanent. Van der Waals forces are not permanent. They are constantly changing, they are constantly moving, and they are super, super weak. So this explains the trend in boiling points of noble gases as we go down. So as we go down the groups, our boiling points increase, and it's actually because the amount of van der Waals forces increases. So as you go down the group, there are more electrons. As a temporary dipole is caused by electron distortion, the more electrons, the greater the distortion, therefore the stronger the van der Waals forces. So that's not saying they're weak. Basically, the more electrons, the more van der Waals forces we can get, therefore the stronger they can be. We also have hydrogen bonding. Hydrogen bonding is one that you come across loads in biology. It is the strongest type of intermolecular force, as it has some character of dipole-dipole interactions and some of dative covalent bonding, but it's still 10 times weaker than a covalent bond. So it can occur when a molecule has a very electronegative atom. So for example, fluorine, oxygen, nitrogen, that has a lone pair of electrons. So remember, the term lone pair refers to a pair of outer electrons that are not involved in bonding. A hydrogen atom covalently bonded to this electronegative atom. So we have this is our example of water. So water is made up through hydrogen bonding, and it makes this polar molecule. So an example of such a molecule is water. So we've got our lone pair of electrons, and we have our strong positive charges from our hydrogen. So if we were going to draw hydrogen bonds, this is how we would draw our molecules. We would show any lone pairs and our partial charges. In biology, you wouldn't be asked to do this, but in chemistry you are. So what you would do is you draw on with dots at your lone pairs, and then you have your show your partial charges above each atom, depending on where the partial charge is located. So that's our 2 water molecules. And then obviously, if we're then wanting to show that the hydrogen bonded together, we would then draw a straight dotted line between the lone pair on one atom and then the hydrogen atom. The bond angle around the hydrogen atom must be shown as 180 degrees. So that must be in a perfectly straight line. The bond angles within water, which is different, are not on 180 degrees, which means that it's a polar molecule. But our bond angle for hydrogen bonding must be at 180 degrees, perfectly straight line. You can get asked to draw these a lot in the exams. If you do not draw them on 180 degrees, you do not get the marks. So quick few questions that you can actually have a pause and have a go at yourself, but I'll go through the answers now. So what intermolecular forces are present between water molecules? Well, they have van der Waals forces, because van der Waals forces are present between all molecules. Has dipole-dipole forces, because water is a polar molecule, and it has hydrogen bonds. And you can also get asked things like this, so show how a hydrogen bond might occur between water and ammonia. So here's an example. That is our water molecule with the free lone pairs of electrons drawn on. We also have our partial charges drawn on, and then we have our straight dotted line showing our hydrogen bond at an angle of 180 degrees. So what I'm going to do is I'm just going to stop there for today. I know I'm a little bit